Hi everyone. Is my slide is visible? Is my slide is visible?
Yes, sir.
Okay, thank you. So yeah, um, good evening all, and welcome to the our very last and the end session of week of the doubt and problem solving session of techniques of material characterization. So we have covered the entire journey, and this is our last because it's the last module, week 12 module, where we will be covering the doubts and problem related to whatever covered in the lecture of week 12. And this is the last week, and I hope that whatever you have learned in this course through lecture, maybe you have got enough knowledge and understanding and the feel of this subject. And I also expect that and I also hope that whatever I have taught you and from my side and whatever I have discussed in these all sessions, that might be helpful for you guys to understand this subject even more better. And if you have any questions or any doubt, and you can ask also. And I think the exams some pattern also came, like whether it is a pen paper or computer based. So as far as my understanding, this is computer based exam will be there. So I think there will be some kind of a short answer writing, and your objective and a little bit subjective and a multiple choice question and some numerical questions like gate and some small writing kind of a questions will be there. But anyway, you guys prepare well and do good in your exam. I do not know that when is your exam, but if you have any question regarding whatever we have covered till now, because this will be our last session, so you can ask if you have any doubt, and if not now, you can also ask in the last. So I hope that this would help you in a way to learn better this subject. So let's begin with our questions for today's, and we'll see that what we have learned in this week. Okay, so so the first question is, in XRD pattern of for crystalline material, temperature diffuse scattering contributes only in peak broadening, peak shift, background of the pattern, and increase in peak intensity. So actually, there is a different kind of a material, as we have learned in the subjects, like crystalline, amorphous, and polycrystalline, single crystalline. So when we get a XRD pattern of this crystalline material, then when there will be a temperature diffuse scattering or some temperature, I mean some temperature effect. So here it is saying a temperature diffuse scattering. So how it will contribute? So can you give the answer for this question if you have something in your mind?
See,
Okay, fine. So the answer is C, background of the pattern. So here, when there will be temperature diffuse scattering. So as you can see in this, XRD plot. So in XRD, what we get usually is the intensity versus 2 theta. So here it is saying no thermal vibration, and here it is saying some thermal vibration. Okay. So it is showing that effect of thermal vibration of the atoms on on a powder pattern. This XRD peaks are showing. So here the temperature diffuse scattering is what? So thermal vibration. Okay, if there will be thermal vibration that cause some general coherent scattering in all direction, which is nothing but the temperature diffuse scattering. Okay, and it contributes only to the general background of the pattern. So here it is asking about how it will contribute on what. So it will contribute to the general background of the pattern, and its intensity gradually decreases with 2 theta. So here, as you can see, the background is changing because here it is at the straight line, but here the it is changing, and also the intensity is decreasing slowly, okay, with 2 theta value. And the contrast, so that's why here the temperature diffuse scattering contributes only in background of the pattern, like this general background of the pattern, and its intensity gradually decreases with 2 theta. The contrast between lines and the background, okay, suffers. So this effect is undesirable one, leading in extreme cases of diffraction line in the back reflection region is clearly distinguishable from the background. So we have to, set up the background, or we have to subtract the background in order to get our XRD pick in the same line, okay. And the temperature diffuse scattering can cause scattering at non-Bragg angle, since the display it is something else it is saying. So here the main thing is the background of the pattern it will contribute, and your intensity of your peak, as we can see, is decreasing by increasing the 2 theta value when there will be the thermal vibration. So this is the main thing of this question. So the temperature diffusion contributes on background of the pattern. So answer is C. Yeah, so the next question is on the absorption factor. So absorption factor is equal to what? 2 mu, 1 upon 2 mu, 2 theta, 1 upon 2 theta. So mu is the coefficient of absorption of the sample, and theta is Bragg's angle. So what will be the relation?
Sir B.
Okay. Okay. So in the absorption factor, the diffracted beam is of lower intensity than, okay, so when there will be diffracted beam is lower intensity than what one would expect from a specimen of no absorption, okay. So here absorption factor is given by, in this case, a theta, and number, so it is number by which the calculated intensity is to be multiplied to allow for the absorption, okay. So this is the absorption factor. So here it is saying that this calculation depends on the geometry of the diffraction method involved. So here in this lecture, you can feel have some, what is the absorption factor. So here this absorption factor A2 theta is equal to 1 upon 2 mu, okay, and independent of theta. So it will not depend in any way with the theta, which is a Bragg's angle. It is only dependent on the mu. And how it will depend? It is equal, or it is proportional to 1 upon 2 mu, okay, and not depend on the theta value, due to exact balancing of two opposing effect, okay. So in powder diffraction, the powder specimen can be considered in the form of a flat plate making equal angles with the so it is saying about this all the optics. I mean how it is, calculating. There will be the specimen, and I naught is the intensity of the coming waves, and this is the diffracted beam ID, and here there will be the angle of 2 theta. So the distance between this is 1 centimeter alpha. So in this way, they have shown some calculation and the derivation. But here the main thing is Gaussian factor is equal to 1 upon 2 mu. And also the absorption decreases the intensity of diffracted beam by the same factor, and therefore does not enter into the calculation of relative intensity. So it is saying that when there will be the absorption, it will decrease the intensity of your diffracted beam. So when your theta value will be the large, the irradiated area is small, but the penetration depth is relatively large. Okay, so here it is asking about the absorption factor is equal to 1 upon 2 mu, as here you can see. Okay, so mu is the coefficient of absorption. So the answer is B. Okay, let's move to the next question. So here it is about the Debye-Scherrer method. We can ignore what in Debye-Scherrer method? Only absorption factor, only temperature factor, both absorption and temperature, or the multiplication and absorption factor. So what will be the answer for this question? Anyone can guess, give some answer? No? Okay. So here in this, where you can find that this in this method, what we can ignore. So, so here it is saying that in temperature and absorption factor, the temperature effect e to power minus 2m and absorption factor which is a theta in cylindrical specimen depend on diffraction angle in opposite way. So to a first approximation they can cancel each other. Okay, so in the d by Schroeder method, so in the first approximation, what is this two effect, temperature effect and absorption effect, so they can cancel each other. Okay, so both will be cancelled and both we can ignore in this method. So in high 2 theta, the intensity of a diffracted beam is decreased very little by absorption, but very greatly by thermal agitation. While in low 2 theta value, it will be vice versa, right? So when there will be the Bragg's angle, which is 2 theta, will be the higher, the intensity from whatever the diffracted beam is coming, that will decrease. Okay, in a very low amount by absorption, but when there will be the thermal agitation, it will be very greatly, I mean it will decrease very greatly. Okay, so this is saying about that. So here we can cancel this both temperature and the absorption effect, both in this method we can ignore. Okay, so here it is saying the two line effect do not exactly cancel one another at all angles. If the comparison of line intensity is restricted to line not differing too greatly in theta value, the absorption and temperature effect can be safely ignored in the d by Schroeder method. Right? So here in the first approximation, we can ignore this both, the temperature and the absorption factor both. So the answer is C. Okay, so let's move to the next question. In XRD, as we increase the temperature, okay, so there will be also some related thermal. The maximum intensity of the peak, so which I already said in few slides back, decrease, increase, or decrease, increase depending on the material, or the remain same. So just give the quick answer for this. What will be the intensity of the peak will happen when the temperature will increase? Anyone? No. Okay. So here, as I said that here you can see. Okay, so here this will be like there is a xrd. When you do xrd, so there is a what you call, that is a um, variation temperature xrd. Okay, so where the temperature will vary and you will get a xrd peaks. So there you can see on your compound, on your material, what will be the effect of the the in how the intensity of your peak will get affected by the thermal process or by the effect of temperature. Okay, so here the thermal vibration of the atoms causes a very slight increase in the breadth of the XRD peak of the diffraction, and the diffraction line are observed to be sharp right to the melting point, but their maximum intensity gradually decreases. Okay, so whatever the maximum intensity will be there, that will decrease when you will give the temperature. Okay, so this is the main thing. So as here you can see of this peak, I think you can see in a much better way that in 30 degrees centigrade the peak intensity is higher. So when you go to the higher and higher temperature, the peak intensity at the this 1000 or the 1075 degree, it is much lower than what we have it 30 degree. Okay, so this is the main thing it is asking. So the maximum intensity of a peak start to gradually decreases when the increase in the temperature. So this is the, you can find it in the variable temperature xrd, this kind of a data. Okay, so let's move to the next question. Identify the material from the below xrd pattern. Okay, so this is also a good exercise. So in a material science or in a metallurgy field or whatever field you have, uh, if you are working in a sort of any sort of a material, you have to go for the XRD for the characterization. Okay, you will have many things. Suppose if you are getting whatever given in the question, there are many peaks which are having a different intensities, and here the intensities is one low and then it comes fall down, and here it feels like nothing. It's coming like this. So how will you uh, you know can give some statement that what could be this material, whether it is a crystalline or a liquid or a monatomic gas or a gas or
Sir,
what yeah, somebody was saying something.
sir, B. B. Option B.
Okay, so
It's
you are
line
saying,
liquid.
okay, so you are saying this is crystalline and this one is liquid and this one is a monatomic gas.
Yes, sir.
Okay, yeah, fine. So let's see. Okay, so whatever you have said, that is correct. So this is for the crystalline material. So in the lectures of XRD, we have seen that how the amorphous, if you have a liquid or the amorphous kind of a material, how it will give your XRD peaks, and if you have a crystalline material, you will get this kind of a sharp intensity peak, and if the amorphous, you will get this broader peak. Okay, and in for the gas you will get this kind of a peak. So here for a crystalline solid, the scattered intensity is almost zero everywhere. Okay, except at certain angle where high sharp maxima occur. So these are the diffracted beams. Okay, in the case of crystalline, when you have amorphous or a liquid kind of a sample, the X-ray scattering curve showing nothing more than one or two broad maxima. So here you can see hardly one or two this broader kind of a peak, not peak, maxima. Okay, for if you have a gaseous material, then the X-ray scattering curve show no maxima. Here you can't find any maxima. Mainly a regular decrease of the intensity will decrease increase in the scattering. So here the intensity will be decreasing like this when there will be the increase in the scattering angle. So this is how. Okay, so this is how you can guess, or how you can have an idea that what sort of a material this. So for crystalline, this will be the XRD. For liquid or amorphous material, this will be your XRD. For monatomic, you will get this kind of XRD, right? So this is that. So yeah, the answer B was correct. Okay, fine. Okay, yeah, this is very good concept when you go for this XRD and all. So full width half maximum, okay, is measured in what? Unit of length. So suppose if I'm saying that for any data, the full width half maxima is this much, and after that, what unit I will use? Unit of angle, arbitrary unit, inverse of length, or unit of length. What I will use? Suppose we measure a length, so what we use? 5 centimeter or 5 meter. So similarly, if I use full width half maxima, so what after this also I will show that how you can measure the full width half maxima. So firstly, tell me that what will be, how I mean, is measured in what? Angle, length, unit, or inverse of length?
Angle.
Angle. Okay. So which is right. So firstly, what is full width half maxima? So when you get a XRD pattern, so here will be your intensity and here will be your 2 theta. So suppose this is one peak. This is in a, I think, magnified. So here full width means, so half maxima. So firstly you will go to, this is the highest maxima, okay, this is I max, and this is your what? Half maxima, I max by 2. Okay, so here you have to, from the base you have to go to the half of the maxima, and there the full width. So full width, it means what? The horizontal. So this is the full maxima, but we have to go to the I max by 2, which is half maxima, and at half maxima you have to take the full width of your peak, right? So this is your full width half maxima. So this is what you will measure? Bragg angle. Or Bragg angle is what? How you will measure the Bragg angle, which is nothing but the degree. Okay, unit of your angle. This is angle. So here you have to measure your full width half maxima in the angle, unit of angle, degree or radians. So the width, here it is saying the width B is usually measured in radians at an intensity equal to half the maximum intensity, and this measured of width in terms the full width at half maxima of, which is nothing but the full width half maxima. So it is measured in the unit of angle. So the answer is unit of angle. Okay, I hope you got it. So let's move to the next. The X-ray line broadening is, in the X-ray line broadening is caused by instrumental source, crystallite size, microstrains, all of this. So do you know how it is caused? So this line broadening is caused by which factor? Okay, so line broadening, the first thing is your instrumental source. So no real X-ray beam is ever strictly monochromatic. The usual monochromatic beam is the one containing a strong K alpha component. Okay, so that will be your monochromatic, superimposed on the continuous spectrum. So here line broadening is also due to the instrumental source, because here uh, the K alpha line has a weight of your 0.001 angstrom, and this narrow range of wavelength in the nominally monochromatic beam, and that will cause your line broadening. since for each value of lambda there is corresponding value of d. Okay, and the next is your crystallite size. So when you will have a different crystallite size, your line broadening will be different. Sorry. So here, as you can see, the result is that small crystal cause broadening. So when you have a crystal which is small, that will cause a broadening of the diffracted beam. Okay, that is diffraction at angles near to but not equal exact at the right angle. So here you can see a different. This is a bulk silicon. This is n-type silicon. So here, for this different, because the crystallite sizes will be the different, you will have a difference in the broadening. So when you have a smaller, so when you have a smaller crystal, that will cause a more broadening. And the strain, when you have a when you create a strain, that will also cause a line broadening, because when you're in your sample, if there will be the strain or the uh, I mean, if you have applied the strain as compared to your normal material, then there will be the change in your parameters, like your d value and your all the things, because the arrangement of atoms will change when you apply the micro or the macro strain. So this will also change in your broadening. So okay, yeah. So this is thing. So the all of this strain, crystallite size, I mean the micro strain or the or the this strain, crystallite size, and the instrumental source, this all will affect the line broadening in the X-rays. So the answer is D. Yeah. So the next is, what can be calculated from the Sarer formula in XRD? What can we get from this formula? Micro strain, crystallite size, lattice parameter, structure factor. Tell me what we can get.
Crystallite size.
Okay. Um, what about others? Do you have any idea what we can get from this?
B.
Okay. Yeah. So yeah, that is correct. We can get a crystallite size. So here you can see that this is the Sarad formula, and to estimate the size of the crystallites from the measured width of their diffraction curves. Here the formula is T equals to zero point 0.9 lambda upon B cos theta B. Okay, so in this calculation we can estimate the crystallite size. Okay, so this is the Sarad formula, so which is right we can get. So here the whether a value. Okay, so here the value of zero point 0.9 or 1 is used depend on the shape of the crystallite assumed to be in the sample. So here it is saying that the order of magnitude of crystallite size effect, lambda is given your 1.5 d1 theta 49. Then for a crystal of 1 diameter, the breadth. Okay, so b value would be about 2 into 10 is to power minus 7 radian, or 10 is to power radian, 10 is, so which is 10 is to power minus 5 degree. Such a crystal would contain 10 is to power 7 parallel lattice planes of the spacing assumed above. So here this is the formula, and here this the crystallite size you can get from this formula. So the answer is B. Okay, so again, it is about the broadening of XRD peaks from instrumental source is due to what? So just now I have showed few slides back that due to the instrumental sources, there will be the broadening in the XRD peaks. So this is due to what? Parallel incident X-ray beams, non-parallel incident X-ray beams, presence of K beta X-ray, or the imperfection in the sample. So
Sir B.
B, okay, non-parallel incident X-ray beams. Okay. What about others?
B.
Okay. Yeah. So in the line broadening due to this instrumental source, so the non-parallel incident X-ray exists in any real diffraction experiment. Since the perfectly parallel, okay, beam assumed an idealization. So this will be for only idealization. So main thing is non-parallel incident X-ray. So this is due to what? Non-parallel incident X-ray beams, because the parallel incident X-ray beams, this is assumed just for the idealization. It will not really exist, right? So here an actual beam of X-ray contains divergent and convergent rays, both. So as well as parallel rays, so that the phenomena of diffraction at angles not exactly satisfying Bragg's law takes place. Okay. So here it is asking about this again, the arrangement that there will be your sample holder, there will be the detector, and the rays are coming and at some angle, and this will be your diffracted beam. So you have remembered that what we call this circle. If you remember perfectly, we called it evolved sphere, something like that. We have studied in our back lectures. So this is what, again the same thing, but the thing is here the non-parallel incident X-rays exist in real diffraction instrument. So the answer is, sorry, the answer should be B, non-parallel. Here it is by mistakenly I put A. Yeah. So the next is in XRD, uh, tensile uniform strain. Okay, when you have a sample which goes under tensile uniform strain. So the causes peak shift from the original Bragg angle. So suppose this is also a good exercise when you have a normal sample and of some material, when I will give you after the tensile, uniform strength. So what could be the change in the XRD peaks you will observe, that whether it will shift left, right, up or down. Tell me. Okay. So when you have unstrained, grain appears on the left and the set of transverse diffraction planes shown is everywhere. And so here it is saying about the, so suppose there will be the no broadening, there is a no strain, you have a center. Suppose we have applied a strain, uniform strain, so your unit cell will also expand in this way, right? So here firstly your shift, your peak will shift to the left. Okay, again, because here this is a uniform strain, when you have applied a non-uniform strain, so the atoms will shift from their ideal position. In that case you will get a big broadening. Okay, so here, but in the question it is asking about the uniform strain. So when the uniform strain will be there, your peak will shift towards left. As you can see here, it is at the exact center, but here at the center, if with respect to this, with respect to the first one, it is at the peak of the maxima is at the left as compared to the no strain sample. So if the grain is bent and the strain is non-uniform, the Bragg plane spacing exceeded, and on the bottom side it is less than this d naught and somewhere in between d naught. So here you will get a peak broadening. So line shifts is the basis of X-ray method for the measurement of micro stress. So when you will have a stress or a strain applied in your sample, depending upon the type of strain, whether it is a uniformly or the non-uniform, you will get a peak broadening either, or the shift in the peak by applying of strain. So the answer is A, left. Yeah. So the next one is, which of the following parameter cannot be measured by X-ray diffraction technique? Okay, so we have done enough knowledge or from the last many lectures. We can measure this, that, and there are several principles or methods. We have seen that and how we are measuring and what is the effect of different factors. So this is a very basic question where it is just asking about what we can't measure. So the first one is the crystal structure, crystallite size, phase transformation, phase diagram, electronic state, Fermi energy, microstrain, and residual stress of the crystallite. So just quickly answer this because it is very simple. Just remember, it is asking that what we cannot measure. It's not about what we can measure.
So maybe option C.
Okay. Okay. What about others?
C.
Okay. Yeah. So, hmm. Yeah. So here this is saying about that what is the possibilities, mean, suppose if I will give you XRD diffraction data, so what I mean, what you can extract from that, what you can identify, what you can determine from that data. So the first thing is phase. We can also get a crystal structure as we have seen in our past lectures, whether it is a FCC, BCC, SCC. So for that, I have also shown that what is criteria and how we can determine that. What is some different there is some rules that H plus K plus L in this type of crystal structure. This should be like that and like that. So lattice parameter determination, crystallite size determination, just few slides back, microstrain and the dislocation structure. We can also determination that what is the effect of there is a peak broadening that it can cause by a strain and all. Residual stress determination also, orientation and crystallographic texture determination also we can do. Phase transformation study we can do, because this all this all will affect your peaks in a some way, so that all we can say okay, this is due to this factor. Phase diagram construction, quantitative phase fraction determination, crystal quality determination, okay, and other also. So there we can extract so many we can extract so many knowledge from your XRD data. So but one thing that we can't do is the electronic state and the Fermi energy. This is something else, and that from the XRD we cannot measure. So yeah, so the answer is C. Okay, so in the XRD pattern for polycrystalline material, in JCPDS file contains a straight line with a definite spacing, broadened peaks, only one broadened peak, a curve with big hump. So I have shown you some, example of how the XRD peak will look like. So you just, it is very simple. So if I will give you a polycrystalline material, then how your XRD peak or pattern will look? Tell me.
A.
Okay. What about others? No. This is very simple. Na? I have shown you a few slides back that it is about when you have a crystalline material, you will have a straight lines with a definite spacing. You will in what case you will have a broadened peaks when you have amorphous or a liquid kind of a sample, then you will have amorphous peak. Only one broad, and also in the case of a amorphous and a curve with a big hump. So when you have a if you will get a very sharp peak, so this is for a crystalline at the definite spacing. So here you can after few spacing you will have this sharp kind of a straight line peaks. So this is for a crystalline material. Okay, here you can see for the amorphous you will have this broad peak. Here this is for the glass. Here you will have a broad peak. Okay, so this is the thing that when you have a polycrystalline or a crystalline material, you will get a definite straight line peaks at a definite spacing, straight lines with definite spacing. So the answer is A. Okay, so the next one is how can we determine the micro texture of polycrystalline material using Kikuchi lines? So what can we use? TMEDS, SCMEBST, XRD, SCMEDS. What?
Option D, Samidius.
Okay. Okay. Fine. What about others?
B.
B. Okay. Others? Okay. Yeah. So here it is about the Kikuchi lines. Okay. So in actually not in Uh, I think somebody has said SCM ADS, but I think we have not. We have covered the SCM part, and Kikuchi line is something different, which you will get. So there is a like EDS, there is a extra setup which is attached in the SCM. So definitely SCM is right, but it is not EDS. This is EBSD. So SCM EBSD. So here this EBSD, you can get a range of information by using EBSD, like what will be your crystal orientation, micro miss orientation is there, grain size you can also measure, global texture, local texture, recrystallized and deformed fractions, strain analysis, substructure analysis, grain boundary characterization, and CSL bounded distribution, slip system activity, phase identification, phase distribution. So there are many things in from the EDS. You can just simply the percentage and the presence of your element, that only you can measure. But EBSD is something else. You can have a lot of informations. So I mean. This is from the here the crystallography orientation morphology of the microstructure can be characterized and it is applied to many industries such as metal processing, aerospace industries. You can use nuclear industries, automotive, microelectronics, and many more. So this is a very uh, just excuse me. So this we can use for a very wide range of application to get a lot of information. So there are many materials which can be investigated by using EPHD. You can use a metal, some alloy or ceramic, thin film, semiconductor, superconductor, intermetallics, a lot of. So but when you will use, you will get a this kind of Kikuchi pattern. So this backscattered Kikuchi pattern from cadmium at 20 kilo electron volt. Okay, so this is from the scientist Shoji Nishikawa and Seishi Kikuchi. They are Japanese scientists. So here, this is your Kikuchi pattern. Okay, height of EBHD. So this you will get in EBHD, SEM EBHD. So the answer is B. The next is Kikuchi lines are produced in SEM EBHD by SE1, SE2, SE3 or backscattered electron. I just showed you the exam, I mean the image, and by the name itself it is very clear, EBHD. I will say you the name, electron backscatter diffraction. Yeah, so it is very simple, it is D. Okay, so here when you will see the lecture and you will try to understand the working principle of this EBHD system, how it will work, and so this is also here the backscattered electron is mainly responsible for your this EBHD. So you will use a BSC or the backscattered electron. So the answer is your D. Okay. So yeah. So this was the questions that I have covered in this lectures. So if you have any doubt regarding this question, you can ask right now because this is our last session, and I hope whatever or you have a doubt regarding any questions or your anything, you can ask now. I will try to answer your questions, or yeah, you can ask if you have any questions or any doubt in any problem till now what we have covered from week 1 to week 12.
Sir, I have one doubt actually regarding numerical questions.
Okay, so which numerical?
So I think many of our assignment are having numerical questions in which
Hmm.
that multiple choice answer is actually choice is given
Hmm.
like a range. For example, 7.9 to 7 point means 7.5 to 7.6,
Uh-huh.
7.6 to 7.7,
Yeah,
7.7 to 7.8. Like that only option is given.
yeah, yeah,
Suppose the answer is actually 7.7 only. For example,
yeah,
it is actually coming in the two range. Say answer C or D. Both
yeah.
it having 7.C as a end and first. So which one should be select? That is what.
So what I will suggest you to go, suppose if the answer is suppose okay, let's see this way. So suppose my answer is 0.200, and option A is given 0.199 to 0.200. Option B is 0.200 to 0.201. So always choose option B. Okay, don't go that side in the, minus side. Always prefer this side because 0.200, which is right. So both A and B are containing. So always choose B, 0.200 to 0.201. Okay, because when you solve any numerical, you there is a not chance. Suppose if I will have a, suppose after that, maybe if you will go to the exact value, if you will put of some constant. So suppose if you will get a 0.20005 kind of a thing, then it will come under 0.201. So that's the reason, because it cannot reduce the value, but there could be some constant or some factor. By putting the value of those factor, it can increase. Okay, so choose this option B. So I hope you got it.
Yeah. Thank
Any
you.
other doubt or some? So when is your exam for this course?
30th.
Huh?
30th.
13. Okay, yeah. So I hope that whatever you have learned in this course, and that will benefit, or that you will have a, a good knowledge and the understanding about this course, that what it is all about and how this characterization is very very important when you go for any field, whether it is a material or a metallurgy or a lot of field. You have to go for the material characterization, and from this basics, okay, many people do a lot of characterization, but the what after characterization, you have to analysis your results. So if you don't have a basic understanding or the knowledge about this course, how you will, analysis your data. So a data analysis is also main part. So for that, this kind of information is very important. Whatever you are getting, suppose it is XRD or a TEM or SEM or optical. So I hope give this course gives you a better, knowledge and understanding, so that you can implement this knowledge in your studies. And I also, take credit that whatever a little bit contribution from my side that I have performed in these lectures, that will help, that would helpful for your assignment solutions. And I hope that I have put I have put my all effort during this week 12. And yeah, that's what I wanted to say. And rest, if you have any questions, you can mail me anytime, or I will try to help you. Or there is a forum also, you can also ask the question whatever doubt you have later on. But yeah, do good in your exams, and all the best. So this is from my side, and if you don't have any other questions, I will stop sharing. And yeah, so our sessions, all the sessions that what we have started from week 1, it's end, or it's complete, it's completed. So thank you
Thank
guys
you.
for joining throughout the session and encouraging me. So I hope I can be your TA for if you will take any other course future in future. So yeah, thank you so much for joining me in all the sessions.
Thank
Thank you,
you.
sir.
Yeah, welcome.
Thank you, sir.
Welcome.